For our Engineering 416 Mechatronics course, we were given the task to create a robot that can both draw an image and analyze a given image to know what to draw. The types of images it would be given to analyze would be a white piece of paper with red and green squares on it that need to be connected to a specific point on the paper. So to do this, the robot needs to be able to do a few things. First, analyze an image for which it can use either a color sensor or a USB camera, like this one is using, and then be able to move an end effector, which is a pen, to draw things. So for this task, we decided to build a Delta robot, which is a robot with 3 arms, each connected to a separate motor, that change the angle of the arms to reach different positions. So for this task, it needs a few things. The first is the robot itself, and the second is the code running on the Arduino in this case, to tell the robot where to go. So, getting into that, first of all I'm going to talk about G-code generation and reading. So to generate the G-code, which is the sets of instructions the robot will follow to draw whatever picture it is supposed to draw, we create SVG files of whatever image it is drawing. These are then uploaded to makercam.com, which is an online website that does SVG to G-code conversion, and set the parameters that fits whatever robot we're using, and then spits out the G-code. And now to read the G-code, we were using MATLAB, which is a fantastic program if you haven't used it before. And we just read the G-code file in line by line, look at all the commands in each line, and then either change internal robot parameters due to those commands or set new target position or current position or something of that nature. Now, since it's obvious that a simple XY position means absolutely nothing to this type of robot, since it just determines its actual position by changing the angle of the 3 motors, we need to do forward and inverse kinematics. Now, forward and inverse kinematics are just converting from the angles to the XY position. And for this type of robot, that is essentially solving 3 triangles. So a first triangle is the end effector connected to the elbow connected to the motor position. So since the end effector position is our target, that's our XYZ coordinate, and our base is known where that is, we know the start position, end position, and position of the elbow, since we know the lengths of both the arm and on the lower arm. Then we have our triangle. We do that 3 times, solve for the angles, and then we have our position. And you can do that in reverse as well, or forward kinematics. So since we know where we are, where we want to be, and that's all from the G-code, and we can convert that into positions the robot understands, now we need to interpolate between those positions. So interpolation is just having your start point, your end point, and then chopping it up into 100 different little pieces in between the 2, and moving in those in order. So there are 2 types of this. The first one is linear, and the second one is arc interpolation. Linear is very simple. It's making a single line and then chopping that up. Easy enough. The second is arc, which is knowing your start point, your end point, and the center of the arc that connects the 2. Now to interpolate between those, first we need to find our starting angle, which is just arctangent of using arctangent with our start position and end position. It's just solving a triangle. And we do the same thing for end position, or end angle. And then once we know those, we just find the span, chop that up into how many interpolations we want to do, and just add that to the start angle. And then we have all our different angles. Sine and cosine gives us our x and y, and we're fine. Doing that method in MATLAB, which we were doing, we use arctan2 command, which gives ranges of -pi to pi when given inputs, and that brought a little bit of a problem when we are moving from pi to -pi, or the reverse. The robot will often think that it has to go way farther than it actually needs to be, so some correction for those cases was required. Now, since now we have G-code generation and the robot knows what to do with it, we would need to go into vision code. So this specific robot was using a USB camera to look at whatever picture we were giving it. So that's taking a picture with a camera, and then to turn that into actual coordinates for the robot to follow, we first turn the picture read into an HSV file, which is hue, saturation, and value. It's just something comparative to RGB. And then we use that picture and compare to existing HSV values that we determined beforehand using a color thresholder given by MATLAB. So we just use that to filter out everything we do not want, and use that information to create an image mask, which is just a black and white image that was just our input image filtered. And then with that black and white image, we can look for rectangles, which then represent our red or our green squares. Now, if we know where the position of the paper is relative to the robot, we can just figure out where are the squares relative to the robot, and then we know where do we need to draw. And then that's just a matter of taking point A and point B and doing a linear interpolation between them. And that's what the robot will draw. Now, with the Delta robot, we had 3 prototypes. The first prototype was a just very simple design made out of cardboard, wood, nails, and using servos to move. And it worked fine enough to test the forward and inverse kinematics that we had written already, but the problem with that version was that everything bent and it was terrible. So, it was useful for what it did, but we quickly moved on to something else, which was our second prototype. Now, in the second prototype, we had both the base and the end effector 3D printed, so we would actually know what we were working with and not be using cardboard. And we replaced the arms, which were made of balsa wood previously, with either a 3D printed upper arm or aluminum tubes for the lower arms. Now, this robot had similar problems than to the first one. It bent a little bit too much, especially the upper arms, which told us that we need to replace them with metal of some sort. And the motor accuracy, which we were still using servos at that point, was far too low. They could only move a minimum of 1.8 degrees, which is much lower. That's about 200 steps, which is far lower than the accuracy we would require for something of this nature. And we also discovered that there was a little bit too much weight for the servos. And that just told us we needed to upgrade the stepper motors to solve the weight problem, to solve the accuracy problem. And with that information, we moved on to our final build. Now this build, which is, you see here, built the frame out of wood, has 3 stepper motors. Each has 200 steps possible, although we are using stepper motor controllers, which allow us to do micro stepping up to 1/16 steps, which reaches us a total of 3,200 steps, or about 0.11 degrees as a minimum change. And we solved lots of problems that we had in the previous prototypes. Namely, the bending was mostly gone. The only bending we have left is just a little bit of play between the joints and at the ball joints. Now this could be easily solved just by using either magnetic ball joints or welding a few things that should be actually welded, but that's not a very big deal. Now the problem that still existed in this robot was the weight of the end effector. So, due to the way servo motors work, is when you turn them to move one step, they turn on, they turn off, and when they turn off, it turned out that they did not have the internal resistance necessary to actually hold up the weight of the end effector. So whenever we try to move it, the weight of the end effector would pull down, it would enter free fall and just collapse. Which is a big problem because whenever we try to move this, it just goes boom, which is bad. So at this point, we did not have much time left for the project, about 1 week, and everything but the movement of the robot worked, so we decided we're going to throw this out the window and do something else. We could have technically solved the problem by doing a complete redesign of the bottom section of the robot and adding in torque screws to the motors to just make the weight of the end effector not actually apply to the motor itself, but to apply to the torque screw and worm gear in between, which would solve all the problem we had there. But due to time constraints, we went a different route, which is building an entirely new robot, which is this. So, this is a hanging plotter, which is actually very similar to the Delta robot that we had before, in the sense that you are just doing forward and inverse kinematics to solve triangles. So the design of this robot is there are two motors, each connected to a spool of fishing line, which you cannot see on the video, but it runs from here up to these hooks and down to this end effector. And we can change the position of the end effector by either adding more line or removing more line to go up or down. The forward inverse kinematics of this work by having our end position, our start position, and then we know what kind of radius or hypotenuse, if you're solving for a triangle, this is, and then just if we know our xy position, we can calculate what length this needs to be. Now, if we know what our current length is, we know how often do we need to turn the motor to reach our desired length. And in this case, this is an open loop robot, so all the information stored of where we are currently, what type of lengths we have currently, that's all stored in the Arduino, and we have no actual feedback. And this was mainly due to time constraints. We really should have encoders attached to the motors to keep our actual position set. So this motor worked fairly well. One unfortunate thing was that our USB camera setup that we had would not work for this case unless we built a very long arm out from the front to mount it. So we decided to just do a completely different method for color sensing, which was a just RGB color sensor mounted in the end effector, which I don't think you can see on the camera, but no matter. So what that does is it just sends RGB values to our Arduino, which we then compare to allowed values to detect, are we looking at red, are we looking at green, and the end effector will just move left and right, hit all the squares, and find out where is green, where is red, and then we can use the MATLAB code for the G-code interpolation and all of that that we made for the previous robot and just plug it in, which worked fine. So this robot can draw, and you will see a time-lapse briefly of it drawing a SFSU logo. And yeah, thank you for watching.